Swayam Prabha. Digital India. Educated India.
Hello and welcome to lecture 46 of the course Theory of Computation. In the previous lecture we saw time complexity, and we saw the complexity class P, which corresponds to the class of problems or languages that can be decided in deterministic polynomial time. Right? So now in this lecture we will start seeing non-deterministic polynomial time. Okay. So before getting into non-deterministic polynomial time, we first have to understand what is the time complexity or running time of a non-deterministic Turing machine, right? In the case of a deterministic Turing machine, the time is fairly clear because a specific input, it's a deterministic Turing machine, it takes a specific number of steps, right? The running time or the time complexity was given as a function f, right? Based on the length of the input. So the Fn, the running time, is defined as the maximum time it takes or the maximum number of steps it takes on any input of the same length n, right? In the case of non-deterministic Turing machine, this is the same. The running time is the maximum number of steps, right? Fn is the maximum number of steps it takes on any input of length n, right? However, there is one additional thing. In the case of a deterministic Turing machine, there is only an input takes a fixed number of steps. Here there are several possible computation branches, right? There are several possible computation branches, and all of which may be of different length. There could be different branches of different length, right? So for instance, you could have branches that end very quickly. There could have branches that go a significant take a significant number of steps, right? So but we define the running time to be running time of a specific input. So this is all for a specific input to be the maximum number of steps taken by the longest path, right? So if this is a specific input and this is the configuration tree, right, this particular the one that is at the bottom, this particular accepting configuration, the accepting path, right, that comes some way like this seems to be the one that takes the longest time. So Fn is should be for this particular input should be this, right, the length of this path. But then we take maximum over the for every input, the Fn is the length of the longest path, and then we further take the maximum amongst all the inputs of a certain length, right? So Fn is the maximum number of steps that the non-deterministic Turing machine capital N uses on any branch of its computation on any input of the length n, right? So you have to maximize on all the inputs of a certain length, and for each input all the branches of computation you want to see the maximum number of steps. That's how we measure or we assess the time complexity of a non-deterministic Turing machine, right? So given this, the rest of the definitions are fairly straightforward once we understand what it takes for how is the time measured for a non-deterministic Turing machine, right? So similar to d time tn, we have n time tn, right? So d time tn was the set of all languages that can be decided in tn time for a deterministic Turing machine by a deterministic Turing machine. So n time tn is a set of all languages that can be decided in order tn time by a non-deterministic Turing machine. So it is exactly the same. The only difference is in this n in the definition n time tn, and the fact that here we have an ntm instead of a dtm, right? So just like we have d time to tn, which is a class of all languages that can be decided in order tn time by a deterministic Turing machine, we have n time tn, which is a class of all languages that can be decided by an NTM, a non-deterministic Turing machine, in OTN time. And just like we had P, the class of all languages that can be decided by a deterministic Turing machine in polynomial time, we have NP, which is a class of all languages that can be decided in polynomial time by a non-deterministic Turing machine, right? So it's exactly the same, but we have, instead of P we have NP, and we, instead of D time we have N time. So definition for P was union of all k equal to 1 to infinity D time n power k. Here we have N time n power k, the class of all languages that can be decided by a non-deterministic Turing machine in polynomial time, right? So later we will see that NP has a characterization in the guess and verify model also. So, but for now I am just mentioning this. Right? So guess and verify model is when you make the non-deterministic choices right at the beginning of the computation, right? Anyway, we will first see some examples. So the first example is something that I described briefly in the previous lecture. It's a language called subset sum, right? So we are given two things, a set S of integers and a target sum T. Okay. The question is, so S is a set consisting of x1, x2 up to xk. The question is there a subset T? So here the subset is written as a subset of the indices such that, such that the subset, the elements of the subset sum up to the target sum T, small t, right? So here the subset is written, indicated by the indices. So if the subset is 1, 3, 5, then the corresponding subset is x1, x3 and x5. But the question is the same. Is there a subset of S that sums up to T? Right? Is there a subset that sums to the given sum? Right? So let me describe. So let us first describe a very direct brute force approach to this problem. Right? So if we have to do it with a deterministic Turing machine, one possibility is we try out. So this is a naive approach, right? You try out all possible subsets. So given that there are k elements of this set, the number of possible subsets is 2 power k, right? We try out all possible subsets, and for each subset you check whether the sum is equal to t. And if you find a subset whose sum is equal to t, you say yes, this is a yes instance. Otherwise you go through all possible subsets and you don't find any subset which sums to t. At which point you say no, there is no subset that sums to t. But then that requires you to do check 2 power k subsets, right? So, or 2 power k minus 1 subsets or whatever, right? There S has k elements, there are 2 power k possible subsets, right? So this is a deterministic algorithm that I just described, but it takes 2 power, you have to check 2 power k subsets, and for each 2 power k subset you have to verify. So that requires some addition, etc. So that may take some polynomial time, etc., which I am not really measuring, but it takes an exponential time in the number of elements of S, right? However, now let me describe a non-deterministic Turing machine, non-deterministic approach for this, right? So one approach is we non-deterministically select or reject each element of the set S. So we come to x1, you either select x1 or reject x1, right? So I've described it in a tree here. So first we decide to include x1 or exclude x1, right? So left means including, right means excluding. And then so whichever way we go, we decide to include x2 or exclude x2. And even if we exclude x1, we have the same two options. And then whichever way we go, we decide to include x3 or exclude x3, and so on. So this, now we keep building this tree, right? And now at the end we will have we will be asking the question, should we include xk or exclude xk, right? And we will have altogether we'll have 2 power k such paths, right? Starting from the left, the leftmost such path which where everything is included, and the rightmost path which is basically an empty set, no element is included, and everything in between where some things are included and some things are not, right? And for each of these, so now we have these non-deterministic choices. So we walk through x1, x2, etc. And at each point we non-deterministically decide to accept or include xi or not include xi, right? So this results in 2 power k possible branches of computation. And then at the end, you just add up. So let's say over here, you just add up, right? Check if sum is equal to t, and then accept or reject accordingly, right? So which is what I have written here. We not deterministically decide to select or reject each of x1, x2 up to xk, and then add the selected xi and verify if they add up to t, right? If they add up to t, we accept, otherwise we reject. So that's pretty much it. That's a very simple algorithm, right? And it's not very difficult to see that this is correct, right? If there is a subset, right? So we are going through all possible, so there are 2 power k possible subsets checked here, right? So 2 power k possible branches. And if there is a subset that sums to t, that will correspond to some computation branch here, and that will get accepted, which means the non-deterministic Turing machine accepts this instance. If this instance was a no instance, meaning there is no subset that sums to t, then all possible computation branches, will reject, because none of them will. So by assumption, no subset sums to t, so everything will reject. Right. If there is a yes, if it's a yes instance, there is some subset, and the branch corresponding to that subset will accept, right? So this is clearly a correct non-deterministic approach, right? But let us see the time taken. So we have to first this step, the non-deterministic selecting or rejecting each one of them. This takes order k time, right? So this takes order k time, right? Or in fact, it's actually not even OK, it's just directly k time. And then you add up the selected xi and verify if they add up to t. So this also may be something like order k time, because there are k numbers maximum, so it takes order k time. So this whole thing runs in order k time, right? But it's I'm talking about non-deterministic running time, right? Not the deterministic running time. In non-deterministic running time, if there is a correct approach, so we don't have to like add up the lengths of all the branches. If there is a correct approach, the machine will find it. If this is the correct accepting path, the machine will find it, right? So the running time is order k for the non-deterministic Turing machine. It's a fairly straightforward algorithm, right? So the approach is clear. We non-deterministically select or reject each xi, and then so we are left with some subset. We add up the elements of the subset and verify they add up to the desired sum. If it is adding up to the desired sum, we accept. If it does not add up to the desired sum, we reject, right? So if there is a subset which adds up to the desired sum, there is some computation branch which will lead to an acceptance. If there is no subset that adds up to the desired sum, then all the paths will reject, which is exactly what we want in a non-deterministic Turing machine, right? And also this running time is order k, which is polynomial in the description of the input, hence subset sum is in NP, right? Hence subset sum is in NP. It takes polynomial time by a non-deterministic Turing machine. However, I cannot say that subset sum is in P, because the deterministic algorithm that I described took 2 power k time, so which is not polynomial in the description of the input, right? So there was a deterministic algorithm, but it took more than polynomial time. Okay. So the next language is 3-colorable. So what is 3-colorable? So 3-colorable is given a graph, we are asking whether it can be colored using 3 colors. Given a graph, so maybe one example is this. So this is a yes instance. Right, so this graph can indeed be colored using 3 colors. Let's say red, green, let's say blue, right? This can be colored using 3 colors. So if you look at any edge, the endpoints do not share the same color, right? So that is the requirement. So how can we check whether this is, given a graph, how do we check this? Again, I will explain the brute force approach, which is deterministic. So for each vertex, so how many assignments are possible? Let's say red, green and blue are the three colors. So if the graph has n vertices, right? So suppose the graph has n vertices. Maybe I'll just move this down a bit so as to make some space. Okay. If G has n vertices, brute force takes 3 power n time, right? Because each vertex has 3 possible choices of colors, red, green and blue, and then it takes 3 power n time, and at the end of so there are 3 power n possible assignments, and then once the assignment is completely assigned, we need to go through all the edges. So that takes, let's say there are m edges, 3 power n multiplied by m time, right? So maybe I'll just say that 3 power n multiplied by m time, which is not polynomial, right? Brute force, by that I mean deterministic approach, takes 3 power n times m time. However, let me just describe. So maybe maybe I should actually write it slightly above. Okay, brute force takes 3 power n multiplied by m time, right? This is deterministic. But the non-deterministic approach is the following, right? So there are similarities to the approach that we followed here, right? So what we do is we walk, let's say the vertices are 1, 2, 3 up to n, right? So we go to the first vertex, we non-deterministically assign a color red, green or blue, right? Then we go to the second vertex, we non-deterministically assign a color red, green or blue, right? So there are 3 options for each vertex, and we non-deterministically assign one of these options. And at the end of that computation path, we have made some assignment. And then this assignment, we deterministically check whether this assignment constitutes a proper coloring. So meaning you go through all the edges of the graph and see whether the endpoints is there any clash between the colors of the endpoints. Right. So this takes, actually the first step takes order n time, this takes order n time because we have to walk through n vertices, and this step takes order m time because where m is the number of edges. Okay. And if the graph is indeed 3 colorable, meaning if there is a correct 3 coloring, one of these multiple computation paths will lead to accept, right? If the graph is not 3 colorable, whatever you try, there will be some edge with a clash. So all paths will lead to reject, right? So what I'm saying is that the running time of this non-deterministic algorithm is order n plus order m, which is order m. Let's say, assuming the number of edges are more than the number of vertices. So the running time is polynomial. Hence, 3 colorable is also in NP. So maybe I'll just use a different color. Right? Because we can do it in this much time. Whereas the brute force takes exponential time. So this is yet another instance of a problem where the non-determinism really seemed to help, right? So now let me make, so we saw two examples. One is subset sum and another one is 3 colorability. Both we followed a similar approach. We non-deterministically made some choices and then we verified it. In this case, we non-deterministically assigned the coloring and then we checked whether this coloring is proper. In the earlier case, we non-deterministically chose a subset and then checked whether the subset added up to the required sum, right? Right. Right. So there was a similarity in both of these things. Anyway, we'll come to that a bit later. One point that I want to mention is a comparison between the classes P and NP, right? So first of all, any deterministic Turing machine can also be considered as a non-deterministic Turing machine, because non-deterministic Turing machine has the capability to make multiple choices for a given configuration. So each configuration, there could be multiple next moves possible, right? So delta can be a function that maps to more than one, maps to a set, so it can map to more than one possible option. So a configuration can have multiple possible successors, valid successors, but multiple possible, it could also be one successor, it could also be 0 successor, right? So a deterministic Turing machine can also be seen as a non-deterministic Turing machine, just that I am not using multiple successors at any instance, right? So anything that can be done by a deterministic Turing machine, we can do it with a non-deterministic Turing machine also, right? Because I can just have the same machine and view it as a non-deterministic Turing machine. So anything that can be done in deterministic time Tn can be done by non-deterministic time Tn as well, right? Because the same machine works. So anything that can be done by deterministic time n power k can be considered in non-deterministic time n power k, right? So deterministic time Tn is a subset of non-deterministic time Tn for any function Tn. Specifically for the function n power k, deterministic time n power k is a subset of non-deterministic time n power k. Now, if I take union of n equal to 1 to k, or n equal to union of n equal to, union of k equal to 1 to infinity for both these terms, we get p in the left hand side and np in the right hand side. So, union over all k, deterministic time n power k is p, union over all k, non-deterministic time n power k is np. So, this gives us that p is a subset of np. Anything that can be, it's fairly simple, anything that can be done by a deterministic Turing machine in polynomial time can also be done by a non-deterministic Turing machine in polynomial time, right? So p is a subset of np, right? Which is a fairly simple thing to say and an easy thing to see. Now let me come to the question which is very, very famous, called the p versus np question. So it's one of the most famous questions in computer science, certainly in theoretical computer science. And if you have at least heard about computer science in popular science or literature or something, you might have come across this question, p versus np, right? So now we have formally defined what is p and what is np. Both of them are complexity classes. P is the class of all languages that can be decided in polynomial time by a deterministic Turing machine. NP is the class of all languages that can be decided in polynomial time by a non-deterministic Turing machine, right? Right. So that is P and NP. P is polynomial time languages that can be decided in polynomial time by a deterministic Turing machine. NP is languages that can be decided by a non-deterministic Turing machine in polynomial time, right? So sometimes some people who are not really students of computer science end up saying, sometimes they think that NP stands for not polynomial, right? No, NP stands for non-deterministic polynomial time, not for non-polynomial, right? So as somebody who has listened to me delivering lectures in this course and somebody who have taken this course, at least I expect the students of this course to know what is P. P stands for polynomial time or deterministic polynomial time, and NP stands for non-deterministic polynomial time, okay, not non-polynomial time, right? So, okay, let me come back to the P versus NP question. So, as I said, P is contained in NP. P is a subset of NP. Now the question is this subset, is this containment proper or is this containment strict? So one possibility is that P and NP are the same. Right? Anything that can be decided by a non-deterministic Turing machine in polynomial time can also be decided by a deterministic Turing machine in polynomial time. So P and NP are the same. So this is what I've depicted here. P and NP are the same set. Or the other possibility is that P is a subset, a strict subset of NP, a proper subset of NP. By that I mean there are languages in NP which are not in P, right? So these are the two possibilities. Is P equal to NP, which is one possibility, or P contained in NP but not equal to NP. These are the two possibilities. So the question is, which of these cases is it? So we know that it is a subset, but is it a proper subset? Are there languages over here? Are there languages over here? Or P and NP are equal? One of this has to be the case. So we don't know. So the answer is that we don't know which one of these cases is the correct one. Even now we don't know, right? So this question was first kind of asked around 50 years back. Even now the answer is unknown, right? So it is one of the biggest open questions in computer science, and certainly in theoretical computer science. And it has got a lot of attention by a lot of computer scientists and also a lot of people who are not computer scientists. One of the it was one of the so-called millennial problems. So there was an American institute called Clay Math Institute who offered a prize of $1 million for if you solve any of there was a list of 7 open questions, and if you solve one of them, they promise any one of them, like each one of them, they promise $1 million to the person who solved it. One of those questions is the P versus NP question, right? So first of all, we don't even know which one is the case. Even if we know, there is no proof, right? So many people believe that the second is the correct situation. Many people think that P is not equal to NP, but it is still unknown what is nobody has an approach, right? Nobody has actually been able to show that. So to show that P is not equal to NP, one has to figure out a language which is in NP and show that it is not NP. Right? To show that P is equal to NP, we'll see some techniques, or we'll see some more theories soon, which will help us develop a theory for this. Right? So this is a big open question, and it is said that many things like the cryptographic systems as of today will collapse if it is shown that P is equal to NP. Right? So it has some other significance as well, not just as a curiosity of an open question, right? This was first asked by Stephen Cook in 1971, and later by or almost in parallel by Leonid Levin, right? By Cook and Levin, two people who posed this question independently. So in those days, the thing was that we didn't have internet and email was not there. So it was very possible that somebody in one part of the globe works on some problem, and somebody who is in some other part of the globe also works on the same problem. They even publish it in their, let's say, their own journals or whatever. But then by the time the first person reads that the second person has also worked on it, by then both of them have built the theory and published it, right? So it was asked around 50 years back, right? And it's still kind of unknown. The answer is unknown. We don't know which one is the correct case, right? In fact, as I said earlier in the previous lecture, that the paper by Jack Edmonds also talked about difference between polynomial time and exponential time. Many of these ideas probably were kind of in the air, so to speak, right? So people thought about these ideas, but maybe not formalized. In fact, it was later discovered that in a letter in 1956, Kurt Gödel had asked John von Neumann the questions which are similar in nature, not so formal. It was like just a letter, not a formal theory or a formal academic paper. But he had asked about P versus NP, or a question which would imply or which would relate to P versus NP to John von Neumann. Right? So There is a Wikipedia page for P versus NP, and you should certainly have a look at it. So the thing is this, so just to give a slightly more philosophical overview, if you look at three-colorability, a non-deterministic Turing machine is able to guess some coloring and verify it, right? Whereas a deterministic Turing machine has to kind of check, like determine the three coloring in a brute force manner. So one is about just verifying. Non-deterministic Turing machine is able to magically guess the correct coloring, and it just has to verify. Whereas deterministic Turing machine, it has to go through and identify the three coloring as well. So one is about actually finding out the three colorability, right, where the deterministic Turing machine. Non-deterministic Turing machine, it's about verifying the three colorability, right? So P versus NP can be thought of as actually computing something versus verifying something. Or another way to think about it is like if you are like a music composer or something, right? Being able to compose the music versus being able to appreciate the music, right? So both of them, you feel that it should be easier to verify than to come up with the answer, right? So that's one reason why people feel that P is not equal to NP, meaning P is the latter is the case. This is the case. So it's like asking, is deciding something the same as verifying something, right? So that's the kind of very, very high level overview about the P versus NP question. It's one of the most important problems. Please have a look at the Wikipedia page or other resources. But now, as somebody who has taken this course, I want you to know what is P versus NP. So P is polynomial time or deterministic polynomial time. NP is non-deterministic polynomial time. Okay, so and not non-polynomial time, right? And the question is, are they the same? So P is contained in NP. The question is, are they the same, or is P a strict containment in NP? And the answer is, we still don't know.